am Sabia Bhagwan, contributing teacher, Department of Education, Shivaji University, Kolhapur. I am going to discuss about waves and optics, in which the wave properties of light. First, what is light? Light is a form of electromagnetic radiation that is visible to human eye with the wavelengths ranging from 400 to 700 nanometers. It travels at an incredible speed of 3 into 10 raised to 8 meters per second in vacuum. This is the fastest speed in nature. As shown in this diagram, light is an electromagnetic wave. It consists of oscillating electric as well as magnetic fields that are perpendicular to each other and also perpendicular to the direction in which wave travels. But what makes light truly fascinating is its dual nature. On one hand, light behaves as a wave. This is clearly demonstrated in a phenomena like interference, diffraction, polarization. A classic example is a Young's double slit experiment, where light produces an interference pattern, something only waves can do. On the other hand, light also behaves as a particle. It is made up of tiny energy packets called photons. This is proven by photoelectric effect explained by Albert Einstein, where light ejects electron from a metal surface. This behavior cannot be explained by wave theory alone. So light is neither just a wave nor just a particle. It has a dual nature. It behaves as a wave while traveling through the space and as a particle when interacting with matter. This wave-particle duality is one of the fundamental concepts of modern physics and forms the foundation of quantum mechanics. Now I will discuss Newton-corpuscular theory. This theory was proposed by Sir Isaac Newton in 1704. According to Newton, light is made up of tiny discrete particles called corpuscles. These particles are emitted by luminous sources such as the sun or a candle. Newton suggested that light travels in straight lines at a very high speed. This explains why shadows are sharp and well defined. He also believed that these corpuscles have a mass and kinetic energy. According to him, vision occurs when these particles strike the retina of our eyes. Newton further proposed that different colors are due to different sizes of corpuscles. For example, he assumed red corpuscles were larger than the blue ones. However, the theory had limitations. It could not explain wave phenomena such as interference, diffraction, and polarization. It also incorrectly predicted that light travels faster in denser media. Because of these drawbacks, the wave theory proposed by Huygens later replaced it. In a conclusion, although Newton's corpuscular theory was not completely correct, it played an important role in developing the modern particle concept of light, which we now call photons. Huygens wave theory of light. This theory was proposed in 1678 by Dutch physicist Christian Huygens. It directly challenged Newton's corpuscular theory. While Newton considered light as a particle, Huygens proposed that light behaves as a wave. According to Huygens, light spreads through space in the form of waves similar to sound or water waves. Huygens believed that light could not travel through a vacuum. He proposed the existence of invisible, weightless, and highly elastic medium called a luminiferous ether, which filled the entire universe. According to him, light was a longitudinal vibration traveling through this ether. One of the most contribution of Huygens' principle is that it states that every point on a wavefront acts as a source of secondary spherical wavelets. These wavelets spread forward at the speed of the wave. The new wavefront is formed by drawing a tangent or envelope to all these secondary wavelets. A wavefront can be defined as locus of points that have traveled the same distance in a fixed time, although the concept of ether was later rejected. Huygens' wave theory successfully explained reflection, refraction, interference, and diffraction. It became a major foundation for the modern understanding of a light as a wave. Now I will explain the properties of a light. The first property is reflection. Reflection occurs when light strikes the surface and bounce back into the same medium. According to law of reflection, the angle of incidence is equal to angle of reflection. The second property is refraction. Refraction happens when light passes from one medium to another medium, such as from air to water. Due to change in speed, the light ray bends. This bending follows Snell's law. Next is dispersion. When white light passes through a prism, it splits into a constituent colors, violet to red. This happens because different wavelengths bend by different amount. Another important property is interference. When two light waves overlap, they combine to form a bright and dark fringes. This proves the wave nature of a light. Then we have a diffraction. Diffraction is a bending of a light near the edges of obstacle. It also supports the wave behavior of a light. Finally, the polarization. Polarization shows that light waves vibrate in a particular direction. This property confirms that light is a transverse wave. These properties together demonstrate that the dual nature of a light and form the foundation of wave optics. Now, I will briefly introduce three important wave phenomena of light. The first is interference. Interference occurs when two or more light waves overlap or superimpose to form a new wave with a different amplitude. Depending upon how the wave combine, they can produce bright regions called a constructive interference or dark regions called a destructive interference. These phenomena strongly supports the wave nature of light. The second phenomena is a diffraction. Diffraction is the bending of light around the sharp edge or small openings and its spreading into geometrical shadow region. This effect becomes noticeable when the size of obstacle or slit is comparable to the wavelength of light. Diffraction again proves that light behaves as a wave. And third phenomena is polarization. Polarization is property of a transverse wave. It describes the geometrical orientation of the oscillations of a light waves. Since only transverse waves can be polarized, polarization confirms that light is a transverse electromagnetic wave. Together, interference, diffraction, and polarization provide strong evidence for the wave nature of light. Now, let us understand the superposition principle, which is the basic principle behind the interference. The superposition principle states that when two or more waves reach the same point in a medium at the same time, the resultant displacement at that point is equal to the vector sum of displacements of individual waves. In simple words, we add the amplitudes of a wave algebraically, as shown in figure. First, consider constructive interference. When the crest of two waves meet the crest, crest to crest and trough to trough, their amplitudes add up. If each wave has an amplitude A, the resultant wave has an amplitude 2A. Next, consider destructive interference. When the crest of one wave meets the trough of another wave, they cancel each other. If both waves have an equal amplitude A, the resultant amplitude becomes zero. This produces darkness or minimum intensity. So depending upon how the waves combine, we get either reinforcement or cancellation. This principle forms the foundation of many wave phenomena, especially interference pattern.